Good morning everyone. This is Saranya S, Assistant Professor, Department of Physics from St.Josephs College of Arts and Science for Women, Hosur. Now I am going to discuss about applications of Schrodinger's equation. So these are the applications. First one, the particle in a box. Second one, potential step. Third one, the barrier penetration problem. Fourth one, linear harmonic oscillator. Fifth one, hydrogen atom problem. So first one, particle in a box. So look at the picture. Consider a particle moving inside a box along the x direction. The particle is bouncing back and forth between the walls of the box. The box has potential barriers at x equal to 0 and x equal to L. That is, the box is supposed to have walls of infinite height at x equal to 0 and x equal to L. The particle has a mass m and its position x at any instant is given by 0 less than x less than L. The potential energy V of the particle is infinite on both sides of the box. The potential energy V of the particle can be assumed to be 0 between x equal to 0 and x equal to L. By using the Schrodinger's time independent equation, we can get the energy value or eigenvalue En is equal to n square h square divided by 8m L square or A square. For each value of n, there is an energy level and the corresponding wave function is psi n is equal to root of 2 by a sin n pi x by a. So we can substitute the n values in both eigenvalue and eigenfunction. Afterwards we can get the particle in a box A is equal to root of 2 by L. So the normalized wave functions of the particle, psi n is equal to root of 2 by L sin n pi x by L. So these are the different eigenfunction values after substituting the value of n. N is equal to 1, 2 up to nth. So second one is potential step. So the potential function of a potential step is defined by V of x equal to 0 and V naught. So V is equal to 0 at x less than equal to 0 and V of x which is equal to V naught at x greater than 0. The electrons of energy E moves from left to right, that is along the positive direction of x-axis. It is desired to find the eigenfunction solutions of the time independent Schrodinger equation. Some particles may be reflected by the potential barrier and some transmitted. The first and second terms of the Schrodinger's equation represents incident and reflected particles. The reflections are which is equal to magnitude of reflected current by magnitude of incident current. So transmittance means T is equal to magnitude of transmitted current by magnitude of incident current. Two cases may arise: E greater than V naught and E less than V naught. In the case 1, In case 1, E greater than V naught, when E greater than V naught and P2 is equal to root of 2m into E minus V naught is real. So here reflectance R is equal to P1 minus P2 of whole square divided by P1 plus P2 whole square, and transmittance will be 4P1 and P2 divided by P1 plus P2 whole square. In the case 2, E less than V naught, when E less than V naught and P2 which is equal to root of 2m into E minus V naught, which is imaginary. Here the transmittance will be 0, reflection will be 1. So this is the potential step. Here are the equations for region 1 and 2 from the Schrodinger's equation, and the condition will be V of x equal to 0 and V naught. So at the region psi 1 and at the region psi 2, which is equal to represented here. So third application is the barrier penetration problem. Consider a beam of particles of kinetic energy E incident from left on a potential barrier of height V and width OA equal to L. V greater than E, and on both sides of the barrier V is equal to 0, which means that no forces act upon the particles there. This potential is described by V equal to 0 for x less than 0 and V is equal to V for 0 less than x and less than L at the region 2. V is equal to 0 for x greater than L at the region 3. Let psi 1, psi 2, psi 3 be the respective wave functions in region 1 and 2 and 3. So look at the picture. Here psi represents incident and another side psi exists which represents the transmitted wave. So at the region 1, the condition psi 1 is A e power I alpha x plus B e power minus alpha ix, and A is the amplitude of the wave incident on the barrier from the left, B is the amplitude of the reflected wave in region 1, F is the amplitude of the wave penetrating the barrier in region 2, and G is the amplitude of the reflected wave from the surface at A in region 2. C is the amplitude of the transmitted wave in region 3, and D is the amplitude of the reflected wave in region 3. Here transmittance T is equal to C square by A square, and reflectance will be B square by A square. So reflectance T is equal to 16 into E by V of 1 minus E by V exponential minus 2L by H by 2 pi root of 2m into V minus E. So this is the formula for the barrier penetration problem. Here mass m is equal to 9.1 into 10 power minus 31 kg and energy E is equal to 5 electron volt incident on the barrier with the height V is equal to 10 electron volt. Here 1 electron volt, which is equal to 1.6 into 10 power minus 19 joule. H cross will be 1.06 into 10 power minus 34 joule second. Thank you.